Okay. So, so let's see what a fusion is. Okay. So it's actually important structure which is used in the field of earth sciences, and has been exploited for different ore deposits, different groundwater deposits, and also in mineral deposits also. And so let's see what a fusion is. Fusion is a zone within the earth crust or the upper mantle that has been strongly deformed due to the walls of rock on either side moving in the opposite direction or the same direction with a velocity difference. That means these shear zones are shown along which the rocks are moving or slide past each other. So shear zone is a zone of strain localization. That means the motion between these two rocks or the two plates, uh, uh, the stress got accommodated by these strain zones. So that means shear zone is a byproduct of the strain localization by the rock movement or the different plate movement. So fusions can be found in micro scale to macro scale. We can see the offset and the smearing of the material. In the figure to my left, we can see the black colored rock got smeared out because of the lateral movement of these two blocks with just half centimeter of offset. And to my right, you can see the offset is around 500 kilometers. So the shear zone to my right is around a 500-kilometer long shear zone, and the shear zone to my left is a shear zone in millimeter to centimeter scale. So let's see how we can identify shear zone in field in rocks. A shear zone is a zone of strain localization. So we should expect strongly deformed rocks as these rocks are accommodating strain. So to find out a shear zone in field, there are some key points. The first one is we should expect deflection of fabrics as one fabric enters the shear zone. Here you can see the black colored rock. We should expect it should move along this red line, right? But as the black colored rock enters the shear zone, this zone of strain localization, the trend of this rock change and it follows the shear zone trend. And the second key point to identify shear zone is the rocks within a shear zone should be strongly deformed. That means we should get strongly deformed fabrics within a shear zone. And the third key point is the in a shear zone we should expect grain size reduction because the rocks within a shear zone are accommodating strains. So because of strain localization, one should expect grain size reduction in a shear zone. So let's see this another field example that depicts a typical shear zone. You can see here the zone between these two white line is the shear zone. You can see there is considerable grain size reduction within this shear zone. You can see the white patches outside this shear zone. These are big blobs of white minerals, and within this shear zone you can hardly see the bigger grain size. So there is considerable grain size reductions within the shear zones. And from the drag effect, we can also see there is a change in fabric. You can see the red lines represent the fabric outside the shear zones, and the flat lines here are actually the fabric within the shear zone. You can see when the fabric enters the shear zone, it tends to reorient itself along with the shear zones. So from this drag effect, we can calculate the sense of shear of this shear zone. Here you can see the top block moved to the right relative to the bottom block. So you can see the top block is moved to the right and the bottom block moved to the left in this particular outcrop. And we can also identify fusion from microscopic observations. This is one of the photomicrographs. You can see there is a shear zone, and as I've already explained, that shear zone is a zone of strain localization. We should expect grain size reduction and strong fabric development. So you can see in this photomicrograph, the rocks found within the shear zones are strongly deformed, and there is a considerable grain size reductions. And these kind of rocks found within the shear zones are called as myelonite, which literally means rocks formed formed in a grinding mill. That means rocks have suffered considerable amount of grinding. So we can see in this photograph the grinding of the rocks within these shear zones. We can see in the intact zone the grains the grains are of bigger size uh, as the rocks as the grains enter the shear zone. We can see there is a considerable change, a considerable reduction in grain size within the shear zone, and there is also a strong development of a planar fabric, which in geological term we call this as a foliation, which is a planar fabric that developed in a shear zone. So let's see how these shear zones behave at a different depth. As we go deeper, we know that the temperature will be higher, and hence the rheological properties of the rocks will change. At around 300 degrees centigrade, mostly the silicate rocks enter the brittle ductile transition zone, which is at around 10-kilometer depth. So with depth, the thickness of the shear zone gradually increases, because we are entering from brittle regime to brittle ductile transition zone to ductile transition zone. That's why the shear zone thickness gradually increases as we go deeper in the earth crust. And below 10 kilometers in a shear zone, the rocks accommodate the strain in brittle regime. Above 10 kilometer, the rocks will accommodate the strain in brittle regime. However, below 10 kilometers, the rock will deform ductily, because the minerals within the rocks are in a ductile phase. So during the deformation, those minerals will accommodate the strain in a ductile phase. So let me show you some of the field examples in both in outcrop photographs and also some microscopic images of the rocks taken from a shear zone at different depths. So the first photograph, this one, is at when the rocks are deformed at a brittle regime. You can see the shear zone thickness is very there is a thin shear zone thickness, and you can see the powdery materials found within the shear zone, and this also we can see in thin sections also. And at this depth, the shear zone rocks are actually cohesionless powdery material. So so in a fault gouge zone, and when the rocks are deformed in a brittle regime, the rocks loses its original cohesion, and because of there is no cohesion, the fluid can easily enter a shear zone and precipitate in veins also. And at a relatively deeper position, we found cataclastic type of rocks with broken fragment of rocks that can be seen both in out of scale and also in microscope. And these rocks are not cohesionless material, but they have a strong cohesion. So these rocks can behave as a strong material. At a much deeper part, in the ductile regime of the rock, we expect the mylonites with strong foliation appeared here appeared represented in the red lines. We can see the strongly formed myelonitic foliation at a greater depth. So this can observed in outcrop scale and also observed in microscopic structures. You can see the minerals are aligned in a plane marked in these dotted red lines. Right. So the myelonites formed at a deeper portion of the Earth's crust are classified into three different types based on their matrix content. The matrix is the ground mass of a rock. When we are grinding these rocks, how much ground mass we are forming. Based on those ground mass, the myelonites are classified into three types. The protomyelonite, where you can see the phenocryst or the large crystals, large minerals. You can see the concentration of minerals is greater than 90%. So that's somewhat, sorry, less than greater than 50%. So that's a protomyelonite where the matrix content is very less. So these classification, the protomyelonite, mesomyelonite, and the ultramyelonite classification is based on the amount of strain the rock has accommodated. So based on the amount of strain the rock had accommodated, we expect the grain size reduction. So more there will be strain in the rock, so more will be the grain size reduction. So in the ultramyelonite, we can see the rock has accommodated maximum amount of strain. So there is a higher degree of grain size reduction in the ultramyelonite compared to the mesomyelonite and the protomyelonite. So this is a classification based on the strain intensity. So as a shear zone is a zone of weakness, so that weakness will facilitate fluid circulation, and hence that shear zones are good for groundwater exploration and also for mineral and ore deposit exploration. For example, this is a map of South India where we have a number of gold deposits. For example, the famous Kolar gold deposit, Hatti gold deposit, and Hiragudini gold deposit. All these gold deposits are confined within the shear zones. In the map, the whole region is part of a shear zone. You can see the Kolar gold field is also confined within the shear zone, and from the Kolar gold field, the gold exploration has been extracted for more than 100 years. We can also see the veins within this shear zone from the Kolar gold mine. You can see there are numerous veins within the shear zone from the Kolar gold mines. The golds are actually present within these veins. The white material you can see in these photographs, and these photographs are collected from these Kolar gold mines, and particularly from the vein material. And you can see native gold in the photomicrographs, and these are collected from the Kolar gold mines. And this is another example of a mineralized shear zone in India, the famous shear zone known as the Singhbum shear zone. There are a number of minerals found within this erosion. For example, apatite, copper, molybdenite, nickel, uranium. The famous Jatuguda mines is within the erosion. There are also several reports of gold occurrences within the erosion. So we understand that these erosions facilitate fluid activities and hence resulted mineral deposits and ore deposits. As the CO zone is a zone of strain localization, the common notion is that this is a zone of weakness. However, few recent studies suggest that in few exceptional cases, the CO zone can be act as a strong zone rather than a weak zone. So sometimes the CO zone cannot facilitate fluid activities. So the CO zone will be devoid of mineral deposits and ore deposits. Let's see some other aspects of the shear zone. As the shear zone accommodates the strain, these are the zones responsible for earthquakes. With the application of stress, the rocks accommodate strain. If the applied stress exceeds the strength of rock, the rock will break. And this sudden break of rock will release the stress. This sudden release of stress in the rocks cause ground shaking, popularly known as earthquakes. One of the famous example is the Nepal earthquake that takes place in a Himalayan shear zones. Here, marked in the yellow dot, the Nepal earthquake actually killed over 9,000 people with over $10 billion of property damage. So these situations are very critical, both in terms of societal importance and also in terms of economy of a country. So let's see, this is the last part of the presentation where I will show how the plate tectonics and fusions are connected and how these plate tectonics and fusions have greater implications both in terms of societal applications and economic applications. This is a type example of a convergent plate boundary where you can see one plate subducts beneath the other plate. The subducting plate is the oceanic plate and the overriding plate is a continental plate, right? You can see the subducting oceanic plate released fluid at depth at around 100 or 200 kilometer, right? So, the convergence of the two plates create shear zones in the upper plate because of direct stress marked by these two white arrows. You can see because of the convergence, the stress got accommodated in multiple planes and resulted in development of shear zones. So the released fluid from the subducting plate moves upward because of the buoyancy force, and the shear zones at the continental crust facilitate, because these are weak zones. These weak zones facilitate fluid to migrate, and these migrating fluids can result in ore deposits. For example, porphyry ore system. So the porphyry ore system formed because of the driving because of the subducting slab release the fluid, and the CO zone concentrate those fluid in terms of ore deposits, right? This is a zoomed portion of the earlier figure that depicts how the fluid enters the CO zone. As you can see, the fluid released from the magma enters the CO zone, and as the zone is a weak zone that facilitate the fluid, and the fluid moves gently to the surface, and that fluid flow interact with the surrounding rock and resulted in number of mineral deposits. And plate tectonics and shear zones are combinedly responsible for earthquakes also. The plate motion applied stress to the plate boundaries. In the plate boundaries, because of the stress, the shear zones are formed to accommodate those stress related to the plate motion. So accommodation of the stress in the shear zone resulted in earthquakes. This is an example from Himalaya, particularly regarding the Nepal earthquake. You can see the northward motion of the Indian plate resulted in the Himalayan mountain belt and a series of shear zones to accommodate the stress because of the northward convergence of the Indian plate. You can see these different shear zones in the cross sections. The 2014 Nepal earthquake was originated in one of these shear zone in response to the northward motion of the Indian plate. That means the earthquake is directly related to the Indian plate convergence, Indian plate collision with the Eurasian plate. So these are few take-home points from this presentation. The first point is the plate tectonics is crucial and controls life on Earth. The second, plate tectonics also control the recycling of necessary elements on Earth because of the plate motion. And plate tectonics and shear zone combinedly control the temporal and spatial distribution of fluid path and hence the different type of mineral deposits. And plate tectonics release different fluids and the CO2 help them to migrate to the top of the crust and precipitate in terms of mineral deposits. I think that's all for the presentation, and thank you all for the attention. And I'm expecting a lot of maybe a lot of questions or suggestions. Yep. Any question?
Dear participants, the session is open for a question answers. If you have any question, please ask.
Any question?
So we can move toward the conclusion.
Yep. Sorry. Sorry.
Sir, if no participant having any question, we'll start with the conclusion.
Start with the conclusion.
Yeah.
I don't understand. Beg your pardon. Hello.
Yes, sir.
Can you please repeat?
Sir, if no participant has any question, we'll conclude the session, sir.
Okay. I can draw true inferences. Either they have understand everything, or maybe I'm not able to explain. Yeah, you can conclude the session. Yeah.
Thank you, sir, for accepting the invitation for the speaker of the session. And I hope all the participants has learned the concepts taught by sir, the concepts of plate tectonic, its hypothesis, working of a plate tectonics, overview of a shear zones. Sir has nicely explained how the impact of convergent plane boundaries and shear zones impacting the earth surfaces. I hope all of us will get benefited from these knowledge. Thank you, sir, for sharing your valuable knowledge with us. Thank you very much, sir.
Pleasant smile. Thank you. Thank you.
Dear participants, the attendance link is shared in the chat box. Kindly fill the attendance.